Hello, I'll be speaking about the topic of Gamal crypto system, and this will be my DA3 for the subject blockchain and cryptocurrency technologies. So let's understand that cryptography provides secure end-to-end communication by employing encryption and decryption. The encryption algorithm converts the input, which is a plain text, into an encrypted output ciphertext using a key. The key must remain secured and unknown to the attacker for the system to stay secure. The two types of crypto systems are symmetric cryptography, where there is only one shared key used for both encryption and decryption, and asymmetric cryptography, like where there are two keys, private key and public key, where one of the keys is for encryption and the other for decryption. For asymmetric crypto systems, we require public key encryption to start the communication. One of these public key encryption schemes is the Gamal encryption based on the Diffie-Hellman key exchange protocol for symmetric ecosystems. So let's go for an introduction. So L-Camel encryption is a public key crypto system, and it uses asymmetric key encryption for communicating between two parties and encrypting the message. The crypto system is based on the difficulty of finding discrete logarithm in a cyclic group, that is, even if we know GA and GK, it is really difficult to compute GAK. In cryptography, the L-Camel encryption system is based on the Diffie-Hellman key exchange. It was described by Tahir L-Gamal in 1985. L-Gamal encryption is used in the free GNU Privacy Guard software, recent versions of PGP, and other crypto systems. The digital signature algorithm is a variant of the L-Gamal signature scheme, which should not be confused with the L-Gamal encryption. L-Gamal encryption can be defined over any cyclic group, capital G, like multiplicative group of integers of modulo n. Its security depends upon the difficulty of a certain problem in capital G related to computing discrete logarithms. And now let's talk about the algorithm. So the algorithm has three parts, and it consists of three components. The first component being the key generator, the second component being the encryption algorithm, and the third part being the decryption algorithm. So let's talk about the practical uses of this first. Like most public key systems, the L-Gamal crypto system is usually used as a part of a hybrid crypto system where the message itself is encrypted using a symmetric crypto system, and L-Gamal is then used to encrypt only the symmetric key. This is because asymmetric crypto systems Like Gamal are usually slower than symmetric ones for the same level of security, so it is faster to encrypt the message, which can be arbitrarily large with a symmetric cipher, and then use Gamal only to encrypt the symmetric key, which is quite small compared to the size of the message. Let's go to the first part of the algorithm, which is the key generation. So let's say first party Alice generates a key pair as follows. Generate an efficient description of a cyclic group. So generate an efficient description of a cyclic group G of order Q with generator small g. Let E represent the identity element of G. Choose an integer x randomly from the range 1 to q minus 1, and after that compute the value h, which will be equal to g to the power of x. After this, the public key consists of the value capital G, small q, small g, and h. And Alice publishes this public key and retains X as a private key, which must be kept as a secret and it won't be shared with anyone. And it's a very important part of this whole process. After that, we talk about the encryption algorithm. A second party, basically the receiver, Bob, encrypts a message to Alice, message M, capital M to Alice, under her public key, capital G Q G H as follows. He maps the message M to an element M of G using a reversible mapping function. Then he chooses an integer Y randomly from the range of 1 to q minus 1. Then he computes the s, which will be equal to s raised to the power y, and this is also known as the shared secret. After that, he computes c1, which is g raised to the power y, and then c2, which is m into s. Then Bob sends the ciphertext C1 C2 to Alice. Note that if one knows both the ciphertext C1 C2 and the plain text M, one can easily find the secret S, since C2 into M raised to the power of minus 1 is equal to S. Therefore, a new Y and hence a new S is generated for every message to improve security. For this reason, Y is also called an ephemeral key. Then the last part of this uh, crypto system is the decryption. Alice decrypts a ciphertext C1 C2 with a private key X as follows. First, she computes C1 raised to the power x, which will be equal to s. Then, since 1 equal to g to the power y, c1 to the power x equal to g to the power xy equal to h to the power y, and thus it is the same shared secret that was used by Bob in encryption. Compute S inverse and the inverse of S in the group G. This can be computed in one of the several ways. If let's assume capital G is a subgroup of multiplicative group of integers modulo n, where n is prime, modular multiplicative inverse can be computed using the extended Euclidean algorithm. An alternative is to compute S inverse as C1 raised to Q minus X. This is the inverse of S because of Lagrange's algorithm. Let's see it in a bit more detail. As you can see that this is the inverse of S because of Lagrange's theorem. Since S into C1 raised to the power Q minus X is equal to G raised to power XY into G raised to power Q minus X into Y equal to G raised to the power QY equal to E to the power Y equal to E. Then after that we compute M, which will be valued as C2 raised to the power S minus 1, and this calculation produces the original message M because C2 is equal to M into S. And lastly, we map small m back to the plain text message capital M. The security of the L-Gamal scheme depends on the properties of the underlying group capital G, as well as any padding scheme used on the messages. If the computational Diffie element assumption or CDH assumption holds in the underlying cyclic group G, then the encryption function is one way. It is the decisional Diffie element assumption DDH which holds in G, then L-Gamal achieves semantic security. Semantic security is not implied by the computational Diffie-Hellman assumption alone. L-Gamal encryption is unconditionally malleable and therefore is not secure under chosen ciphertext attack. For example, given an encryption C1, C2 of some possibly unknown message M, one can easily construct a valid encryption C1 to C2 of the message 2M. To achieve chosen ciphertext security, the scheme must be further modified, or an appropriate padding scheme must be used. Depending on the modification, the DDH assumption may or may not be necessary. And let's talk about the efficiency of this crypto system. So L-Gamal encryption is probabilistic, which is very different from RSA, and it means that a single plain text can be encrypted to many possible ciphertexts, with the consequences that a generally L-Gamal efficiency produces a 1:2 expansion in size from plain text to ciphertext. Encryption under L-Gamal requires two exponentials. However, these exponentials are independent of the message and can be computed ahead of time if needed. Decryption requires one exponential and one computation of a group inverse, which can, however, be easily combined into just one single exponential. Let's see the code implementation of L-Gamal encryption using Python. So first we import random and math from POW, and then we generate a random integer from between 2 to 10, and after that we define the function GCD, which returns the each safe of two numbers, and we keep this so that we can use it later. Then the first part is generating keys, and it will take in an input queue, and it will generate a key which will range from 10 to the power 20 to q, and while the GCD of q and key is not equal to 1, we'll keep on generating random integers from range 10 to the 20 to q and store those on key, and at the end we'll return key. Then we also write the function to calculate the power of a number. Then we write one of the most important functions, which is for the symmetric encryption. It takes in four input like we had discussed: message, Q, H, and G, and we store an empty array called end message, and after that we generate the key for Q, and we calculate S and P with power H, K, and Q, and G, K, and Q. For I range from 0 to length of message minus 1, we'll append the message of I into the empty array that we had defined previously. And after that, for range 0 to length of the encoded message minus 1, we'll take up each letter or character and multiply it and set it as equal to odd of that character, and we'll return that character and p. Next we define the decrypt function, which will again take in four inputs: the message p, key and q, and it will first compute h will be the power of p, key and q, and for range of 0 to len of encoded message minus 1, we'll continuously append the chr of integer casted encoded message of I divided by h, and we'll keep on attending this to another dummy array, and in the end we'll return this array. So let's study a bit about the Gamal encryption. So based on the DH protocol, the Gamal encryption was named after Tahir Gamal, as we earlier saw. So suppose A wants to send a message to B, the first router require take up two things, two public fixed parameters P and G, where P is a 2048-bit primary number and G is generated in the range of G but greater than 1 but less than P minus 1. The recipient of the message B will pick a random number x, the range of greater than 0 and less than P minus 1, compute x equal to G to the power x mod P. Here x is B's public key which it broadcasts to everyone, and x is B's private key which will be kept a secret. Now that its public key is well known to A and A wants to send a message M to B, A will pick a random number R in the range 0 less than R less than P minus 2. To encrypt the message M, A will be computing the ciphertext for calculating its public key as R equal to G raised to the power x mod P, and A then will calculate the shared key K minus x to the raised to the R mod P. A will encrypt the message M by computing S equal to M into K. The ciphertext format is R, where R and S numbers lie in the range of 0 to P minus 1. E will send out the cipher key text to R, S to B. B will decrypt the ciphertext by first computing R, S mod B. Upon calculation, this result in the message M sent by A. The Next time he wants to send a message to B, he will choose a new random number R and give a new public key each time. However, B will use its long-term public key, which was calculated previously. The illustration depicts the above-mentioned steps as follows. So, as you can see from the illustration, the security of Elegant encryption depends on strategy that a user uses a new random number each time it has to send a message. This way, one-time pad is used only once, combined with model explanation is one-time pad strategy is just as secure as using a XOR. So yeah, that's it for Gamal crypto system, and I hope you have a nice